Okay, so the third day of day 8, we're going to do just some more of these application problems. So there's a Ferris wheel. It's built such the height in feet above the ground. So this is whatever number comes out is how far off the ground you are. And it's modeled by this. So there's some phase shifts going on. There's some vertical shifts going on. And all that is this vertical shift just means the axis of the Ferris wheel is up off the ground. You couldn't dig this into the ground and make a Ferris wheel. I mean, you could, but it costs a lot more. But yeah, so this, after 1 second, 2 seconds, see how high you are off the ground. So how long does it take to make one complete revolution? So, that's they're asking for a period. So that's 2 pi over the b, and in this case, it's pi over 10. So it'd be 2 pi over 1 times 10 over pi. So that'd be about 20 seconds. So it's a pretty fast moving Ferris wheel. It takes 20 seconds to get around, so it must not be very big. What is the minimum height above the ground? So the minimum height, if you go the lowest that any sine could be, any sine function is -1. So -1 times 50 would be -50, plus 53 would be 3. So that's going to be 3 feet off the ground. And really what it is, this is the amplitude. That's how far up and down you go from the center. This is how far it off. So I think you get this thing 53 feet off the ground, but then you got a circle that's 53. I'm sorry, it's 50. That's a terrible drawing, but it's 50. So when you're down here, you got 3 feet difference there when you're going through the Ferris wheel. What is the height of the seat above the ground at the beginning of the ride? So plug in 0. If you plug in 0 up here, you do get 3 at the beginning. And if you plug 2 in, you just practice plugging it in, you get 12.55 feet for 2 seconds. So that's just plugging 2 in up there. In a 1 minute ride, at what times will a person be at the top? Well, if it's a 30-second, it's a 20-second ride. So if it's 20 seconds, you start at the bottom. That means at 10 seconds, you hit the top. So after 10 seconds, you hit the top. And then 20 seconds later, you'll hit it again. So at 30 seconds, you'd hit the top. And then 20 seconds later, you hit it again. So at 50 seconds, you hit the top. And then when it comes back down, so that would be, now you're over a minute. So during the first minute, this is at what times you would hit the top. The next guy here, the length of the day with sunrise. So basically plot these points in here. So pause the video, plot them. I'm going to save some time. I already have a plot done, so I'm going to switch these out and show you my original plot, which I had some mistakes when I was plotting. I got distracted a few times. So I think this is out. I think that's out. But it should make something like this. It's kind of got a curve to it. Now on the curve, there really is no min and max being shown here. Because on these, like you think the first day of winter is supposed to be the shortest day. Well, that's not on here. It's somewhere between this point and that point. So the shortest day happened before the longest day. What happens in June? Well, that's not on here because it's like June 20 something, 23rd, 19, something like that. I can't remember those days. So it's somewhere in between here. So the longest day. So none of these are really the peak or the valleys, but we can get a good estimate. So looking at this data, you think the min and the max, somewhere in the middle in there is going to be like the midline. So that's like our vertical shift, okay? So somewhere in here, and I just took the lowest data to the highest point, and I add them together and divide it by 2. I got 12.15. So 12.15 as the midline. So somewhere at 12.15 is the midline, and it goes up about 2.2, and it goes down about 2.2. So that's when I'm filling this in right here. We're supposed to kind of guess what it's supposed to be. So we'll say this is about, I'm not worried about phase shifts for right now. We can say, we should shift this so many days. So we got, let's see, so about 12.15 was how high above or below it went between, I'll just put 2.22 I have, between 12.15, so about 12.15 is a midline. Sorry, this should be 2 2.22. Why can't I get this straight? So I found the midline somewhere in there. Again, just estimating. And then if I know that this is 365 days to do a full cycle, if I'm trying to find the b, so the period equals 365, and that equals 2 pi over b, and that means b is going to equal 2 pi over 365. So that's what's going to be 2 pi over 365 t. So this is just a rough estimate. Again, I didn't do a phase shift. I should shift this back so that we would want this somewhere where it has like where it hits midline should be back this way. But I'm not going to worry about that so much. Now, if you run a sign regression, so put all this data in the calculator. Let's see, I actually do still have the data in the calculator, I believe. Stat edit, I put all the data in the calculator, L1, L2, go to stat, over to calc, and then sign regression. So you can do a sign regression. I want this L1, L2 for right now. Calculate, and it's going to churn out the answer. Okay, so it's going to churn out the answer. If we copy this down, let's see, this will be y equals 2.24. My estimate was 2.22 times sine, and then it has 0.0167, which if you take 2 pi divided by 365 is very close to 0.0167 t plus, here's my phase shift, minus 1.3. So it says go move it about 1.3 this way, 1.3 months over, let's see, I'm sorry, 1.3 days? Yeah, 1.3 days, because that's what I have on there. And then plus 12.12, which I had 12.15 as my estimated midline. So my midline was a little bit off. But again, you may have different numbers over here, just kind of giving a rough estimate. This one here, user graphing calculator, do the same thing. So put them into the calculator, L1, L2, run sign regression. Practice doing that. I'm just going to give you, here's what I got. 0.52x minus 2.2 plus 46.7. So it's trying to, shifts it back so that it starts at 0. Let's see here, and then use your model in part A to predict the May temperature. So if you want May's temperature, May is the 5th month. So plug a 5 in for x. So we'll say f of 5. Say this is f of x. I got 56.7 degrees Fahrenheit when I plugged it in. Okay, so that's just using sign regression. So no, I'm going really fast. I already put it in the calculator. You're going to have to pause and go back and do that. But good practice. Here, we could do these. Trying to think, pick and choose, but we could do all these. We probably have time. A sound wave whose parent function is y equals 2 sine x has 4 times the frequency and half the loudness. So if you just really want to try to make sense of this, what's the frequency of this guy? So the b is a 1. Remember, frequency is 1 divided by 2 pi. And we want a frequency half of that. So we're going to have to cut this in two. So it'll be 1 over 4 pi. And I got that backwards, 4 times the frequency. So I'm going to take that times 4. So my frequency is 4 over 2 pi. That's frequency, and that needs to equal b over 2 pi if I want to go back to b. So that means b needs to be 4. So the number needs to be a 4 out front. Yeah, so all things being the same, b has to be 4. So it's one of, actually that's the only option, right? 4, let me see. And then it needs to have half the loudness. So half the loudness. And it was a 2 out front, so half that's a 1. So that looks like this guy here. So that'd be my letter B, has 4 times the frequency and half the loudness. Let's see, a certain sound wave has an equation of this. Give an equation whose sound wave has half the frequency. So let's just figure out what's the frequency of this. So this frequency, remember, frequency equals B, which is 10 pi over 2 pi. So its frequency is 5. I want half that, so I want it to be equal to 2.5. So 2.5. So what divided by 2 pi would equal 2.5? So if I multiply it over, that'd be a 5. So cosine 5 pi t, and twice the loudness. So twice the loudness means kind of a 60 out front. So you have a higher amplitude out front there. Tuning fork has a frequency of approximately 270 cycles per second. That's a lot. That's a pretty high frequency. If the vibration displacement is an air molecules by a maximum of 0.22 millimeters, so that's the amplitude, give the possible equation for the sound wave. So it doesn't really tell us where it starts, so I'm just going to go with sine. I want to say this is a sine function. The amplitude is 0.22, and if the frequency is 370, that's going to equal b over 2 pi. So multiply that over, that'd be 740 pi equals b. So that's my b here. So 740 pi t, and that equals y. For this one, I actually graphed these. Well, I guess the first one, we can answer these without graphing it. So what's a maximum and minimum output of the voltages? So here's our voltage. The most this could possibly be. So if I cover this up, any sine function, any cosine would be a 1. So 1 times 25 is 25, plus 25, so it'd be 50. The least a cosine could be is -1. So -1 times 25 is -25, plus 25 is 0. So the highest voltage is 50, the lowest voltage is 0, and this is like alternate current. So the volt goes up and then down and up and down. So we put a lot of volts in, which volts is like the pressure that pushes the electrons through. Think like water pressure. Volts is like the pressure that's pushing the water, whereas current is the actual water, how much water is coming through. So over here is a current. What is the maximum and minimum outputs here? Well, this one, again, any cosine, no matter what the phase shift is, any cosine, the highest can be is 1. So 1 times 0.3 is 0.3. And then the lowest is -1, so it'd be a -0.3. So not a lot of current, but the voltage, the 50 voltage there. Now I graph these. So if you want to go on Desmos and graph them, it says what is the phase shift between the output current and the output voltage. So I just looked for a maximum voltage, and then I looked for the maximum current. I looked how far off they were. So if you want to graph those guys on Desmos and look, it's actually -3 pi over 4 is the difference between them. It's to the right, so it's the voltage hits a peak, and then at 3 pi over 4 later, the current hits a peak. So like there's a push, and then the current catches up. Now how many seconds is that? So if you multiply this out, 2.36 seconds, which doesn't seem right for electricity. I got this off the internet, so I assume it's accurate. I have no idea if it really takes that long for a current to catch up. I would assume it'd be like milliseconds, but it does say function in seconds, so I'm just going to go with what that says. Number 8, Dizzy, who loves the rides, he's on a Ferris wheel such that once the ride begins, his height above the ground is in t seconds after. Okay. So at the start of the ride, how high is he off the ground? So I just plugged in 0 for time and in my calculator, and it's 95 feet. He's 95 feet off the ground. Now, how long does it take to do one complete revolution? Well, so one complete revolution would be your period. Period is 2 pi over b. In this case, is pi over 90. So 2 pi over 1 times 90 over pi. That'd be 180 seconds. 180 seconds. So it takes about 180 seconds for this thing to go all the way around. What is Dizzy's maximum height above the ground? So think any cosine, the highest it gets to is going to be 1. So 1 times 60 plus the 65 out front. So that just means the axis is 65 feet off the ground. So that would be 125. Now, if the ride lasts for 9 minutes, find all the times at which Dizzy is at his maximum height. So first off, I want to find when is he going to equal that maximum height of 125. So 125 equals 65 plus 60 cosine pi over 90 t minus 30. Now notice when I subtract 65 over, I get 60 cosine, and if I divide by 60, it's just going to be 1. So I'm trying to figure out when does cosine, so pi over 90 t minus 30. Now if I do inverse cosine of 1, that's 0. So inverse cosine of 1 is 0. So 0 equals pi over 90 t minus 30. If I multiply this over, I'm going to be multiplying by 0, so that's gone. And then add 30, so t equals 30. And then 180 seconds later, so 210. And I need to go up to 540, basically. So 540 would be 9 minutes. So 210 plus 180 is going to be 390. Plus 180 is 570, which is too much. So there's 3 times, the 3 seconds that he's going to hit that. Number 9, let's see here. The figure to the right shows a Ferris wheel rotating 50 revolutions per hour. Now what is the amplitude? Well, the amplitude on this is going up 20 and down 20 from its center point. So from the midline, so that's 20. So this one's going to be 20. What is the period of the wave? Well, the frequency is 50 revolutions per 60 minutes. So if you reduce that, that'd be 5/6 of a cycle per minute. Well, that is a frequency, so flip that over, so it'd be 6/5 minutes, or 1.2 minutes, or 72 seconds. And then when does point P reach its highest point? If it is at the bottom when it starts. Okay, so it's going to take half of that. The full cycle is 72 seconds. It's going to take 36 seconds to get up there. Says when does it? Well, I could stop there and say 36 seconds, or if you want to talk about every time after that, well then plus 72 in seconds. That would be all the times, where in is just any integer. So hopefully this helps. It is kind of a long video, but you can always fast forward to the parts you kind of already know, or yeah. So if you have any questions, like I said, this is not due until Tuesday night, so we can use some time in Tuesday, or some time in class on Tuesday to answer some questions you might have.